let's continue our analysis of how an existing substituent on a benzene ring affects the electrophilic aromatic substitution reaction. In this video, we're going to be considering the possibility of having a substituent such as anisole present on the benzene ring. I'll be using a nitration reaction again, but also just like in the previous video, this is all going to be true no matter which electrophile we're using. So again, we're going to go through the three different possible mechanisms for this nitration reaction of anisole: the ortho mechanism, the meta mechanism, and the para mechanism. And I'm going to go a little bit faster with these mechanisms since we have a better understanding of the reaction now. Here are the sigma complexes for the ortho mechanism. You might notice that there is an extra one this time. That is because the anisole molecule has a lone pair of electrons on the oxygen atom that's directly attached to the ring, and that lone pair of electrons on the oxygen atom is able to get delocalized down into this resonance structure, which actually moves a double bond out, or creates a double bond outside of the ring and moves that positive charge out of the ring. So that gives us a fourth resonance structure in our sigma complex, which, as you can imagine, is going to be pretty helpful. Like we saw in the last video, the ortho and the para mechanisms are pretty similar to each other. So if we look down here at the para mechanism, again, we see the same kind of thing, that positive charge being delocalized up out of the ring due to the presence of the lone pairs of electrons on the oxygen atom. So 4 resonance structures for the para mechanism as well. And then the meta mechanism, which is always a little bit different, because in the meta mechanism, because the positive charge never ends up in the correct position on the benzene ring, that lone pair of electrons from the oxygen atom is never able to get delocalized down into the ring, which means the positive charge is never able to make its way out of the ring. So again, we want to look at, just like with the last one, we want to look at which two mechanisms are similar and what do they have in common. And again, our similarity is going to be between the ortho and the para mechanisms. This time, in addition to having the positive charges in the same positions on the ring, this time they also have that fourth resonance structure in common. So our ortho and para mechanisms have 4 resonance structures. Now our next question, just like on the last worksheet, which mechanisms are more favorable, which is less favorable? Well, the more resonance structures you have, the better things always are. So the more favorable reaction in this case would be ortho and para, again, because of the 4 resonance structures. And the less favorable would be the meta reaction. A meta reaction isn't bad. There isn't anything bad about it. I'm just going to call it bad anyways. It's just not as good as ortho and para. Meta is less favorable because only 3 resonance structures. So to generalize what we're looking at here, if we add a second substituent to a benzene ring that has an alkoxy group, anything that is like OCH3, like methoxide, which is what we have in this example, where will that substituent go? It's going to go into the ortho position or into the para position, because those are the better mechanisms. If you add a second substituent to a benzene ring with an alkoxy group, will it be faster or slower? It's going to be faster, because putting the substituent on a plain benzene ring only has 3 resonance structures. The alkoxy group allows us to have that 4th resonance structure, which makes it good